Good morning, everyone. I am Catherine Cesco, the Chief Stakeholder Relation and Dissemination at Europe's Rail, and I'm very happy to be here with you this morning to introduce the second day of our Innovation Days for Europe's Rail 2022. So today we will be looking at, like we did yesterday, optimizing the legacy from the Shift to Rail program and making sure that the innovation, the research that you have undertaken, researchers, is taken up by the market, is still visible and is carried forward to be integrated in the system at a later stage. So very happy to introduce this morning first session that will be managed by Sébastien Denis on optimized infrastructure. This session will last from 9:30 to 12. We'll then have a lunch break, and another session will start at 1 o'clock on digital services, which will last until 2. And a third session will start at 3 o'clock until 17:30 on IPX and looking at system architecture and disruptive technologies in particular. I will be back then at 5:30 at the latest with our head of program, Giorgio Travaini, to take conclusions and draw conclusions and look at the outputs from all the presentations that we have today. So enjoy the day, stay on this link because the first presentation will start in a minute on optimized infrastructure with Sébastien Denis. Enjoy.
Good morning, ladies and gentlemen, and welcome to the infrastructure session of the Europe's Rail 2022 Innovation Days. My name is Sébastien Denis. I'm IP3 Program Manager, and I'm very pleased to moderate today's session. Before starting it, I would like to remind some housekeeping rules. So the first one is please note that all the session will be recorded, and so will be also available later on the Europe's Rail website in the coming days. Then, for a smooth session and to avoid any technical issues, we have disabled the microphone and the cameras of all participants. However, we want to hear your question, your thoughts, etc. So we are encouraging you to use the chat function of Teams in order to raise any points you would like to address. The agenda of today for this morning, we have been clustering the different presentations in 3 areas. The first one will be linked to energy topic, the second one on infrastructure, and the third one on YAM, so intelligent asset management. Each cluster will be a part of presentation between 3 and 6 speakers, and afterward there will be a dedicated Q&A session. Before starting the presentation, I would like to invite Felicity Osborne to join me here. So Felicity is the coordinator of the IP3 program. She's working in Network Rail, and she has been the coordinator for the past 3 years. Felicity.
Good morning, everyone, and thank you, Sebastian, for the introduction. So I've worked on the Shift to Rail program for almost 6 years now, and during this time, I've witnessed some great collaboration between partners and projects within IP3, and that's going to be very evident in the results that will be presented to you today. This year in particular represents an exciting year for Shift to Rail, as many of the projects reach their conclusion. Intertempo is the longest running project for IP3, and that's now closing out, having delivered an exciting smart meter designed to improve asset sustainability and energy management, of which you'll find out more about later on this morning. In addition, the project also finalised a large experiment using digital twin and machine learning to improve passenger experience within high capacity stations, and this took place in Warsaw during 2022. And I encourage you to find out more about this in today's presentations. Alongside that, the Intersmart 2 project has also concluded this year and recently held its final event in Milan. One of the main successes achieved by the project this year is the demonstration of an off-the-shelf unmanned ground vehicle controlled using the robotic command and control aspect to technology readiness level 7, which has showcased the robotic maintenance capability, and this is designed to operate during track possessions. This is also going to be featured in this morning's presentation. I'm now going to hand over to the rest of the morning's presentations, and I hope you enjoy the event.
Thank you very much, Felicity, for your introduction word. Then I would like to start directly on the technical content to invite Aneta Tumilovic and Olivier Langlois to join. So Aneta is working as a project manager in Network Rail. She's the coordinator of the Intus Tempo project. And Olivier is the TD leader for the smart metering topic, an electrical engineer working for Alstom. So welcome, Aneta, welcome, Olivier.
Good morning, everyone. I hope you can hear me. Thank you very much, Felicity and Sebastian, for this short introduction. Indeed, I have a pleasure of starting off this session with presenting a couple of very exciting results from Intus Tempo project. And I think I'll just start by telling you a little bit more about Intus Tempo itself. So Intus Tempo project was designed within Innovation Program 3 to address 3 technology demonstrators. Out of those 3, 2 you will be hearing about today. It's TD 3.9 and TD 3.10. And generally speaking, Intus Tempo project was looking into innovative solutions in energy metering, in smart power supply, and innovative solutions for improving future stations. Can I ask for the next slide, please? Indeed, as Felicity mentioned, this is this was the longest project within Shift Rail program IP3. We started in September 2017. This is also one of the biggest projects as well. We've had 18 partners from 11 countries collaborating very effectively and efficiently in this project. The work was divided into 11 work packages, and at the end of the project, we among those 4 packages, we've reached different tier levels between 4 and 6. And today's presentations will be, as I mentioned at the very beginning, around technology demonstrator 3.9 and 3.10. And that brings me to introducing my esteemed colleague, Olivier Langlois, who is actually one of the TD's leaders, TD 3.10, and he will tell you a little bit more about those technology demonstrators. Olivier, over to you.
Yes, good morning, everyone. Yes, I struggled to switch on my microphone. I hope you can hear me well now. So good morning again. Thank you, Aneta. I'm TD leaders for 3.10 smart metering for energy management. And I have the pleasure to introduce both energy-related TDs. Next, please. Thank you. So these these TDs are energy related with power supply and energy consumption topics. If you follow these, you may remember this work has started several years ago now already within Shift to Rail and previous Lighthouse project. Actually, the aim is to make a better usage of electrical energy in railway systems, in particular in the infrastructure part at substations level and power supply. The aim is to improve the power quality and to save energy when possible and also to improve the quality of service, to have the trains sufficiently powered to run properly, of course. So now there's evidence the energy consumption is the cause of the current climate change, as you may know, and the global warming. And this year, even more than the previous ones in the international context, it has raised awareness in people's mind. So we all need to reduce our energy consumption. So the energy saving is one of the challenges of the future, but of the present indeed. So I think we achieved interesting studies and proof of concept demonstrators in this project that will help to reduce and better manage energy in railways. So I take this opportunity to thank every partner from these TDs for their contributions and the very good cooperation we had over the past years. So thank you. And I will, yes, I leave the floor to our next presenters to present more in details the technical outcomes from the project.
Thank you very much, Olivier. Thank you, Aneta, for your introduction on the energy topic. So indeed, we're going to start then the technical content on this cluster, and there will be two presentations today. So among all the solutions that have been developed into the program, we selected two of them. And the first one will be presented by Mahmoud Hassan. So Mahmoud is an energy engineer working for SNCF Réseau in the electrical traction department. Welcome, Mahmoud.
Thank you, Sebastian. Thank you, everyone. I hope you are seeing me and hearing me well. So today I'm going to present the work package number 3 of Intus Tempo. So 3 parts. I'm going to talk about the why of the project, why we are trying to optimize the 25 kilovolt existing system. And part 2, we are talking about the FACT solution. So how do we answer all the challenges the traction power supply is facing? And in the third and final part, we will talk a little bit about the results, some of the interesting results we've obtained during this project. Next, please. So in the beginning, a little bit of a reminder of the 25 kilovolt 50 hertz power supply. The conventional technology today is based on transformers. So we have a transformer-based substation. Usually, these substations are separated with a phase separation section between the sectors. And we have different topologies of connection with the transmission system. It is basically an old concept with passive elements. It is simply and easy to maintain, but however, it raises some of the some challenges that I'm going to explain in the next slide. Next, please. Next, yes, thank you. So the first challenge is the increasing traffic. So in the future, all of the studies show that the traffic will increase, and we as an infrastructure manager, we should answer this challenge by trying and increase the capacity of the system. So what is expected in the pluriannual plan of energy in France, for example, we have we should answer the challenge by optimizing the infrastructure. We should increase the overall traffic, especially the freight transportation, and we should facilitate or facilitate the shift from other modes of transportation like vehicles, classical vehicles. So we should optimize the power supply without necessarily creating new heavy installations. That's why we should optimize the existing ones. Next, please. Another challenge the 25 kilovolt is facing the voltage imbalance. So the voltage imbalance is results from the conventional connection between the transformer substations and the transmission system. A conventional one is connected to a pair of phase, and it draws its power from 2 phases from the transmission system. And these connections are alternated from one substation to another. And overall, we face an unbalance in the voltage at the transmission system. So it raises a questions and a problem regarding the quality of the power. And the operator of the transmission network usually, if we are not compliant with some of the thresholds, he can impose financial penalties. And this phenomenon also can affect other users, other consumers connected to the transmission network. That's why this voltage unbalance should be always be in check. Next. Another challenge is the reactive power. So we are working on AC, traction power supply. So in addition of the voltage unbalance, the transmission operator fixes thresholds of reactive energy exchange with the transmission network. So again, if we have financial penalty, if we have exceeded the threshold, we have additional financial penalties. Usually today we are using some passive elements to answer this reactive power, like and the voltage drop on the line. So these passive elements are okay, but they are limited in their impact. So we need to have better solutions to tackle actively this problem. Next. Another challenge in the phase separation section. So the phase separation section is the separation between two sections, collateral sections. On the 25 kilovolt, 50 hertz power supply, this is add some constraint on the operation of the trains. For example, the driver has to deactivate the circuit breakers, open the circuit breakers when the train is running through this phase separation section. And that leads to decreased power quality and decreased efficiency. So this aspect is related to the topology of the 25 kilovolt power supply. And I think one of the aspects we should consider, when optimizing an existing solution, is to try and eliminate this constraint. For example, in DC traction power supply, we don't have this constraint on the drivers. And when we think of an interconnected system, we don't usually think of separation between the networks. So that's why we need to connect and to connect to make the system interconnected, I would say. Next. So what are the solutions? How we are tackling these challenges? So in work package number 3, we worked on FACTS. So what are FACTS? FACTS are flexible AC transmission systems. So these are power converters that can be installed, connected to the existing system. They can also be an alternative solution to conventional substations. And these are power converters that can actively control power flow, either reactive or active. And when we talk about a smart grid, a smart traction power supply, we should integrate these. We must integrate these technologies. They are very important in a fully interconnected and integrated rail power supply. So we studied 5 systems during Indus Tempo. And in the next slides, we will see the overall results. So these are the following facts. We have static power compensator, STATCOM balancer, and rail power conditioners. These are already existing systems, but we studied them for comparison purposes mainly. Static power compensator acts on voltage, reactive power, and voltage level on the catenary. STATCOM balancer can reduce the voltage unbalance, and rail power conditioner as well by acting on the secondary side of the traction power supply substation. And a new novel system that can allow what we call double-side feeding or interconnected feeding. These systems are railway interline power flow converter and static frequency converter. They can install either they can replace either a conventional substation or can be installed between sections, supply sections. Next. So in WP3, we studied, we based our study on two use cases, two lines in France. The first line, use case number 1, you see on the right. It is a 25 kilovolt line supplied by 7 substations. This line was a pretty good use case because today we face a lot of power quality problems on the line. And it was a good basis, in fact, for studying and evaluating the advantages of facts. The second use case is a line operating on 2 times 25 kilovolt. It's supplied by 3 substations. It has already good power quality, but we studied it because it is a very good way to compare the technology to 2 times 25 kilovolt. Because it is already a way to reduce power quality. So we based our studies on these 2 use cases. Next. Some of the results I will not go in detail in them, but I would be happy to answer your questions later. So in static VAR compensator, we try to mimic what an ideal double-side feeding would produce on a line. So we've done a lot of investigation, especially on Esmeralda simulations and software and Citrax Track Designer. So as I mentioned, it was a basis to compare and to see what are the actual possibilities of the SVC. And we showed in our study that the traffic can be increased, but the investments of SVCs are important. That's why we should discuss better technologies. Next, please. The next system is StatCom balancer. So we've done Esmeralda simulations, and we've done also we investigated the impact of some transients on the operation of the balancer. These were done under MATLAB and PSIM. So we studied some degraded modes, and we showed some of the limitations of the system. Next. RPC, so it's the monophasic converter installed on the secondary side of the transformer substation. As the StatCom balancer, we studied some transient phenomenon like voltage sags, swells. We studied also the active power transfer between one section to the other. And we showed that it has some advantages, and if we tweak a little bit the system and the control method of the converter, we can produce another type of application, which will be presented in the next slide. The RIPFC, so it's the monophasic converter connected that allow double-side feeding, mainly by allowing the active power transfer between one section to the other. All that while keeping conventional substation operating on different phases. We investigated several control strategies. We identified one as being the most promising. And this system, we showed also that it has basically an SVC, static VAR compensator feature, but it also can transfer active power. So we increased the readiness level of the system, and we think it's promising for the next phases of investigations. Next slide, please. And the final system, the SFC, static frequency converter, the triphasic monophasic converter, which is supposed to replace a conventional substations. We've done a lot of investigation, especially the co-simulation one. So the co-simulation investigation was had the purpose to model traction rolling stocks with a converter itself inside of the system, and the control method of, or the controlled software and hardware of the converter. So we showed that double-side feeding is possible without the risk of transit current so the transit loop current between the transmission system and the traction system. So we showed that it allows double-side feeding. We investigated the pilot signal strategy, meaning that the SFC will synchronize with the transformer on the adjacent substation. And we investigated also low frequency oscillations, and we've done an isolation coordination study. which shows what are the evolutions that we should think of when we adapt the protections. So yeah, it's very promising solution and fact, and it can allow double-side feeding into 50 Hertz. Next slide. So finally, the cross-project challenges the investigated technologies are helping to resolve. So our technologies, so the facts, can be solutions to increase the traffic capacity by upgrading the 25 kilovolt line. So they enhance voltage level. They can enhance power quality overall. So we can use them as a way to answer the increasing demand. Improving asset management. When we talk about facts, we talk about smart grids. So these are ways to better manage active power and better manage the energy inside of the traction power supply. So it is a way to improve asset management overall. And they can also allow for future interface with other ways of energy productions like renewables. But yeah, we haven't investigated these aspects, but they are. It is totally a possibility. 25 kilovolt. And finally, the virtual model data. So active facts, flexible AC transmission system are active components. So we gained a lot of experience in virtual modeling because we used several simulation softwares, and we used co-simulations. And yeah, it's we gained a lot of experience regarding this aspect. Yeah, so next, I think I have finished. Yeah, what's next? We will continue investigating the project, especially RIPFC and SFC inside of ERGU, the next phase. And yeah, they are promising solutions to allow double-side feeding. Thank you for your attention. So I will give the floor to the next speaker.
Many thanks, Mahmoud, for your detailed presentation. Please stay with us until the Q&A session on energy. And I take the opportunity then to remind and encourage all participants to use the chat function in order to raise any question or comments to our speakers of today. Okay. So the second presentation on energy will be presented by Smail Ziani. So Smail, you are working for Relenium as an electrical engineer, and you are part of the energy management and asset management unit. So welcome, Smail. The floor is yours.
Thank you, Sebastian. Thank you for the introduction. I will just share my screen for the presentation. So we'll just... Okay. So I'm Smail Ziani. So I'm the leader of the work package for smart metering use cases. And the aim of my presentation is to explain how smart metering can be useful to improve railway energy systems. So I will start just quickly to present our use cases, where we developed the smart metering approach. So we have three use cases. The first use case is a commercial operation use case. This use case is led by Network Rail and is located in the south of London in the UK. For the line Tonbridge to Redhill is the 750 volt DC line. And the aim of this use case is to improve the mapping of energy flows dedicated to the railway system in commercial operation. And also, what is important, I think, for this use case is to obtain a synchronization data between the rolling stock and the infrastructure, of course, to have a better understanding about the energy consumption. The second use case is led by CAF and is stationing and maintenance operation use case. Is located in Spain, in Zaragoza, and for the Zaragoza tramway. It's like for the first use case, it's a 750 volt DC, third rail. And the aim of this use case is to improve the mapping of energy flows for stations, depots, and maintenance facilities. Another also important aspect about this use case is also to prove or to improve also the maintenance operation using predictive maintenance. And the last use case is also led by network care, like for the use case one. It's the electrical infrastructure use case, is located in London, UK. And for the line, London Northwest Coast Main Line, but for this one is an AC system, so 25 kV, 50 Hertz. And this one, the aim of this use case is to develop detection of electrical anomalies using continuous monitoring. And also, of course, a better knowledge of energy mapping for optimization of the infrastructure performance. So now I will just introduce quickly what is smart metering, how we can use it. So of course, for smart metering, we need to start with the sources. So about the data, so the sensors, for example, for the infrastructure, but also maybe for the rolling stock. And after that, we need to collect this data using gateways, for example. Analysis also, but I think what the most important part for your user is about user applications, like using dashboards. An important part about smart metering, of course, is the hardware part, the implementation. So, of course, we need to install some sensors about voltage, current, to have information about the power and energies. So we have also, for example, GPS sensors. And of course, one important part about smart metering, it's also the data logger, the acquisition system to get the data. So we have some examples here about the installation of this kind of smart meters in the three use cases. Also, another important part is also the software part about the architecture of the smart metering solution. So, of course, we start from the data. So, for example, current and voltage measurements, the GPS data. So we have the messaging, the processing, but I think what it is important, it's the user. So we use a database where we can have the storage of the data, and of course, a tool to visualize the data, to create some indicators. So we use for the work package for the Grafana tool. So just to introduce a very quick first results. So here we have a dashboard from the Bushy feeder station for the use case 3. So we can take a look on the live view, the live data from this substation for the different feeders. So we have the consumption of the current in real time, and you have, of course, some indicators, useful indicators like THD, for example, or power factor. So now I will maybe present more in details the impact of smart metering. So I will start with the asset management topic, and I will start with an example about fault detection for catenary system. Yes, this user application is, I think, novel and very useful because we have two novel approaches. So the first one is more about the hardware. So we use a high sampling frequency to get some fault events, some short circuits from the catenary. And I think this approach is very smart because we take the data only when we have an event, a short circuit, before 10 seconds or 20 seconds before and 20 seconds after using triggers. And also we have, I think, a novel approach, a software approach, a novel software approach using a Hilbert transform to calculate the phase shift between the voltage and the current with accuracy, because you have instantaneous phase shift. And like this, it's possible to calculate the impedance of the event and to have better a better accuracy of the location of this kind of event. So here we have an example of the high sampling frequency from the current and the calculation of the impedance with a low value that corresponds of a really high value of the current. And of course, who will benefit? So the train operator, the railway owner, and the passenger. Another interesting impact of smart metering about asset management. So we have also for the use case 2 some interesting approach using machine learning about the track switches to detect and to get more information about failure detection. So we use machine learning to have this kind of information. For example, here we have an anomalous cases detected by using machine learning from the current, and also an example for the energy. So also who will benefit? So the train operator, the railway owner, and the passenger. So now I will talk more about the energy consumption and the demand, of course. So one of the most interesting, I think, user application is the detection of regenerative braking energy using machine learning, and it's possible to quantify this kind of energy. This is for the use case one. So I think it's very interesting approach, and especially about DC. Because like this, it's possible to use only sensors in the infrastructure to detect the energy braking. And like this, it's possible to quantify this energy and maybe to improve the consumption of energy, because it's possible to have more information where it's possible to install some storage, some batteries to get this kind of energy. So of course, who will benefit? So the train operator, the railway owner, and the passenger. Other impact about the demand, about energy losses. So we propose also we integrate in our dashboards the approach about Sankey diagrams. It's very useful, I think, because it's possible to understand better the losses, and of course, it's a very interesting step to improve the energy consumptions, and also it's very useful to have some patterns about the energy, and like this, it's possible to detect some abnormal consumption. So the train operator, the railway owner, and the passenger will benefit about this user application. And I will now talk about another impact. It's more about the software validation. So the real data we use are also very useful to validate or to improve the software tools. For example, here we have the data from the speed from a software tool, and here in the right side you have the data from the sensor, from the GPS. So like this, it's possible to validate or also improve the software simulation, or to modify the educator models used in this kind of software. So the train operator will be benefit, and also the railway owner. So now I propose also to take a look about the impact of smart metering, but with an interactive session to show maybe directly what is our dashboards, how it's possible to be useful for a user, for an engineer. So I will share my screen again for just one moment. Okay, so I will maybe start with this kind of dashboards to have more information about, for example, the current. So here we have live data from Bridgingly. So it's a substation from the use case one for Tonbridge railway line. So it's possible to take a look on the data, for example, from the current, from the feeders. We have also the DC voltage from the catenary, and it's possible to have information in real time and some interesting indicators. For example, we have some information about the apparent power and also the power factor. And I will maybe show also very quickly another interesting user application. Here it's more about use case 3. I just refresh the logging, and I will show you for the use case 3. It's just a reminder, it's more about 25 kV here and 50 hertz. So here, for example, for the month of April 2022, you have information about energy consumption. For example, here we have the power for 1 month. It's possible to zoom in to have more information about the consumption and the peak loads, for example, because you have a high sampling frequency of 1 second to have more information about the peak loads energy. So you have the power. And just to give you maybe a better information about what I presented before about the detection of events like short circuit for the catenary. So we have some triggers, some alarms, for example, for low voltage and high current. And I can show you very quickly an example. So here we have the acquisition of a high sampling frequency with 10 kilohertz from the current and the voltage. So we have the raw data. And we use this kind of raw data from the current and the voltage to calculate, for example, the impedance of a defect. And like this, it's possible to have some information about the location. And also, we add also other indicators, other alarms from, for example, from the THD. So here we can see that the current from the THD is a little bit high. Okay, another example, I think it's very useful for a user to understand how it's possible to create a dashboard or an indicator. Here we are in the database of the work package 4. For example, for the use case 2, we can take a look on the data to just show, for example, some examples. I will just submit to have this kind of data and to show how it's, I think, easy to create for an engineer an indicator or an information. So I'll just take a look on the script from InfluxDB with the script from Influx. I will just copy this kind of script. I will go to the dashboard of the use case 2. I just need to refresh the access. Okay, I need just to add a new panel, for example. So I will just create it and I will just add the script, pass the script. I will just refresh, for example. And now I have access to the data, for example, for the 3 currents from the feeders from the substation 5. I will just save this. And I will come back to the dashboard and I have access to this new panel very easily to have the data, and I can zoom in, I can zoom out on this kind of dashboard. I can change the sampling frequency very quickly, for example, just to put here another information from the data. So if I want to take, for example, 1 minute. And I can refresh and I have the information with better accuracy, for example. I will just come back to my presentation to finish my presentation. Okay. Okay, I will just finish with the addressed cross project challenges. So we have 3, of course: the demand, improving asset management, and the virtual modeling versus the data. So our contribution for the work package 4, it's, for example, for the demand, of course, we have the energy flow information. So we can help to identify opportunities for reducing losses and, of course, improving efficiency of impact using of the timetables or driving style changes. So it's possible to have more information how we can reduce the energy consumption. Of course, the smart metering are very useful because are not non-intrusive, so we don't need to modify the implementation or something like this. What is also interesting is the time synchronization of the data, so we can improve our understanding about energy consumption between the rolling stock and the infrastructure. And for asset management, of course, we have also interesting results about detection of faults, diagnosis also, and some first approach about CBM to, for example, about the switches. For the virtual modeling, so also we have interesting results to validate the software tools, but also to modify the modeling, use it in this kind of virtual software. So I finished my presentation. So thank you for your attention, and I'm available to answer about your question. So I just.
Many thanks, Ismail, for your detailed presentation. And before starting the Q&A session, I would like to invite Mahmoud to join back the virtual stage. So the first question actually will be for you, Ismail. Olivier was presenting in the introduction the current crisis we are currently facing in terms of energy, and you were here properly presenting the current solution in smart metering. So how somehow the solution you are developing in the program could contribute to solve the energy crisis we are facing at the moment?
Indeed, thank you, Sebastian, for this interesting question. So, of course, Intus Tempo can, I think, be very useful for this kind of difficulties, because the first, I think, objective of the Work Package 4 and the smart metering from Intus Tempo is to have a better knowledge, better information about the consumption. I think it's an important step to reduce this consumption, because like this, it's possible to know where we have some opportunities to get energy, to reduce the energy. For example, for the use case 1, we proposed an approach to quantify the energy breaking. So the energy breaking is very interesting. So it's possible to know like this where we can store or where we can install some storage like batteries to, for example, to use this energy, and like this we can reduce the classical energy from the grid. So of course, so I think the first important step and to have quickly information is the quantification of energy, and it's an important I think step.
Yeah. Thank you very much, Ismail, for your explanations. My second question will be for you, Mahmoud. So according to your presentation, and despite all the very good progress you made on the facts topic, I understand that there's still some stage to be made before the product is ready for the market uptake. So I wanted to hear from you, what are somehow the main challenges in the next phase in order to have your solution ready for the market?
Yeah. So in the next phase, ERGU, so we are trying to, we will push the investigation regarding RIPFC and SFC. One of the first challenge for RIPFC would be to choose the readiness level. Would be to choose the appropriate control strategy. So that's why during the next phase we will try and get all the information of the detailed parts of the infrastructure. Because as you know, in IntoSample we've studied 2 use cases, generic ones, and the idea in the next phase is to go on the field and take all the information possible. Regarding SFC, the next investigations would be to also once the use case is defined in the ERGU, it's to maybe site the system appropriately to the use case and test the strategy and the pilot signal strategy a little bit further. Especially from the standpoint of short circuits, oscillations, maybe better, a better or maybe a more complex scenarios on the line. So yeah, that would be, in my opinion, the next phases of investigations we will make in the ERGU. And in addition, and last comment, ERGU should produce a prototype. We are aiming for a site, but yeah, we should, I think, put some attentions on the site. And yeah, once the use case is defined, I think we will define more and better the use case, and that is a condition for the success of the next phase.
Thank you, Mahmoud. Thank you, Ismail, as well, for your participation today and your availability for your presentation and the Q&A session. We are going to move forward now for the next cluster on infrastructure. So basically all solutions related to tracks, switch and crossing, and bridge and tunnels. For that, I would like to invite Pernia Hedlund and Anders Caroline to join me on the stage. So Pernia, you are working for Traffic Verket as a program manager. You are the coordinator of the Into Track 3 project. And you, Anders, you are also working for Traffic Verket in the innovation unit, and you are the TD leaders on bridge and tunnel. So welcome, Pernia, welcome, Anders. The floor is yours for this introduction on infrastructure topic. We do not hear you, Anders.
Okay, so, but you can hear me?
I can hear you, Pernia, indeed. Yeah.
This is strange. Oh,
Anders.
Can you hear?
Yes, we hear you now.
We hear
Please.
you now. Yes.
Apologize, I will compensate and speed up a little bit. Thank you very much.
No problem.
Good morning all. And I will start introducing this TDs. So this section deals with very tangible infrastructures, the components that the trains run on, the structures making line geometries possible, and equipment leading trains to the right destinations. Yes, we are talking about tracks, bridges, tunnels, and turnouts. And the nature of this work is not so much a desktop, it's more laboratory or real site installation. And with that in mind, I'm very impressed of my colleagues in all companies, in the broad European representation, and in all projects that have done a very impressive work. As you all know, laboratory work and site installations were extremely difficult to perform for a period, and the teams have engaged extremely well and not only compensated for the missing time, but also in several cases exceeded, I would say, the already high expectations from the MAAP and so on. We have been working on optimizing existing investments and developing solutions for the next generations. And in a few moments, we will see a selection of solutions recently developed or demonstrated. For me, starting from the Lighthouse projects, it has been a very pleasant journey involving several steps, challenges, and also interesting people. So, Pernilla, would you take it forward?
Yes, I will. Thank you very much. You can take the previous slide. In Intertrack 3, we have three main objectives, and those are to increase availability and reliability, enhance railway performance, and reduce life cycle cost. And we come from a line of projects and are the last one in the series. Our results will be taken forward, but not in an Intertrack 4, but in other projects or programs within Europe's rail. I wanted to show you this picture just to give you a view of the development through these different projects where we started. And the example is the 3MB slab track, which is just one of our demonstrators that we have. It has moved forward with the development from the sketch table, the drawing table, and now just a few months ago, we installed it way up north in Sweden to test it, and it's out there being tested on high pressure loads as we speak, and will be for quite some time. That's just one of the examples that we have. And if we shift to the next one, our goal with the project is to get as many demonstrators as possible. We have some 50 demonstrators in total, of which almost 30 are on a high TRL level 7, which means that they will be tested out in track or in relevant environment, depending on the type of demonstrator. And you will see a few of those here now today. And I wish you much pleasure in viewing what we have done so far. And there is much more to come. We also have a cooperation with the project Into Zone, I should mention, and they have a webinar on January 23rd that everyone should attend because it's closely related to Intertrack 3. Thank you.
Tania, Anders, many thanks for your introduction words on this cluster. And we are going indeed to go now into the details with one of the solutions you mentioned, so the 3MB system. So I'm inviting Carlos Hermosilla to join the virtual stage. So Carlos, you have been working for the past 10 years in the Actioner R&D Center, and you are somehow the co-author of the 3MB system that will be presented today. So Carlos, please, the floor is yours.
Thank you, Sebastian. Yes, so as Sebastian was saying, I'm Carlos Hermosilla. I was deeply involved in the development of the 3MB concept from its very beginning. The 3MB is basically a slab track system. Next, please. Sorry. Yeah, the 3MB is a slab track system composed of precast elements. The idea is that it would be modular as much as possible, so the assembly would be easy and the positioning would be simplified. It has a top-down alignment strategy, so the rails are placed exactly in their correct geometry, and then the difference between the substructure and the rail is gapped with in situ mortar, fast-setting mortar, so that it takes less than 24 hours to harden. It was designed to allow all kinds of traffic from the very heavy to the very fast. And it's based on the concept of the pin system, which we can see in the bottom right-hand corner. So all the blocks are fixed to the base slab with this contraption. It's composed of an embedded nut in the base slab, a cylinder of steel or a tube, and a steel bolt. Each block has 2 of these, and the idea would be that the blocks can move vertically but are restrained horizontally. This was required for 2 reasons. The first is that the system incorporates an additional elastomeric layer between block and slab, so it's good for the absorbance of vibration and noise. And the second reason is that the bolt that I've previously mentioned can be removed, and so the blocks can be extracted laterally without having to jack the rails in case there's needs for repairing the system, exchanging a block, or resurfacing, which is one of the great advantages of this system. It's a slab track system that allows resurfacing. Next, please. And after 8 years of development, we finally reached the point where we could install it in actual working track. So thanks to the collaboration with Trafikverket, we were able to get a small track section of 50 meters in the far north of Sweden, in the area of Gransjö. It's a heavy haul line. It's known as the Malmbanan, the iron ore line, with up to 32 tons per axis, which I think it's record in Europe. The assembly was made on a traffic line that was in operation, so we had to do it very, very fast. And the conditions of the weather are going to be quite extreme when the winter comes. It seems it goes down to minus 40 degrees. We had to do everything in just 96 hours because we had to reopen the line as fast as possible. And next, please. To make sure that we were able to accommodate to those 96 hours, we made an assembly test in the beginning of June. We tried out the system to make sure that we were able to assemble it in the fastest and most efficient way. Next, please. Yes, that doesn't mean we didn't find some inconveniences when we were installing. So we were supposed to excavate just 20 centimeters underneath the track to install the insulation layer that you can see in the lower left picture. But instead of that, we had to excavate more than a meter because what we found is what you can see in the right-hand top picture. So a lot of boulders of more than 1 meter in diameter. That caused some settlement problems down the line. But at the same time, it gave us the opportunity to demonstrate that the system can be resurfaced more or less easily. Next, please. Here are some pictures of the assembly. The system originally was thought out to be installed first the base slabs and then the blocks. But we made some tests and we discovered that they could be assembled in full modules. Each module is 4.8 meters long and it has 8 blocks. And after all the modules were in position, which didn't take a lot of time, it was about 20 minutes per module. Once all the modules were in position, the rails were placed and the leveling of the system started. In order to level the system, what we used is a device we denominate false sleepers. Next, please. There are this yellow contraptions that you can see in the picture on the right. And basically the idea is that these false sleepers are attached to the rail. And they have some lateral and vertical screws that allow the positioning of the system. And once the rails were in place, we were able to pour the mortar to, as I said before, bridge the gap between the rail and the block. Next slide, please. The pouring of the concrete was performed by night because we really were very short on time. We had to press on. In this picture, you can see the false sleepers in place. The formwork for the mortar and the kind of contraptions that you used to help the mortar go into its place. Next slide, please. And here is a short movie that Traffic Verkehr prepared with more information and some, yeah, there we go.
Within the EU's railway research programme, Shift to Rail, a new type of track system has been developed. It can be described as a hybrid between ballasted and slab track systems. The new track system is more operationally reliable and requires less maintenance work than the older models. It's much faster to build and install, and current maintenance methods work as well. The unique thing about the new construction is that it's made of modules, which allows you to replace components that break or fix settlements easier and faster than today. Overall, it leads to increased certainty when calculating the life cycle cost. The track system is tested in regular traffic on Malmbanan. The full-scale field test is carried out over a distance of about 50 metres at a place in northern Sweden called Gronsjö.
Coming out in track is important and necessary. However, safety is the most important issue when we are out in track. This is a collaboration in between the infrastructure manager, the industry and the academy. We are here to evaluate the performance of the track system.
The demonstration will last for almost 2 years until 2024. The entire life cycle is tested from installation to operation and finally decommissioning. Everything monitored on site and via continuous digital diagnostics. The work to develop the new track system has taken almost 10 years, and it's adapted to really heavy freight traffic, up to 32.5 tonnes axle load. The new track system is also adapted for high-speed train, up to 400 kilometers per hour.
With the construction of this demonstrator, we have reached a critical milestone in the development of the 3MB system. After 8 years of design, development, testing and optimization, we're finally ready to install in real operational track. Not only that, but this track, the Malmbanan, offers extreme conditions with very heavy axle loads and very low temperatures in winter. With the data we recover, we will validate the system and know that it is ready to offer it to the market.
With this demonstration, in collaboration with Shift to Rail and Traffic Verket, Sweden are at the forefront of research and innovation for a new track system. A track system with increased lifespan that saves both money and time, as well as contributes to increased accessibility and punctuality in both Sweden and the rest of Europe.
Okay, I think we can go back to the presentation now. Just a couple more slides. So as the video said, we're monitoring this in real time. So we installed some dynamic and static structural sensors, basically accelerometers and strain gauges. And all these equipment is connected to 3 computers that are currently up in the north of Sweden in Gronsjö, connected to the internet, and we can access those data remotely. Next, please. And here is an example of what we're getting from those data. This is the double integration of the accelerometers in the rail, slab and block. And you can more or less see how the deformations are distributed in the 3 levels. Next, that will be all. I think I've been able to fit it into my allotted time. Thank you for listening.
Many thanks, Carlos, for your detailed presentation and also the videos that are very well explanatory the solution. So thanks for that, Carlos. We're going to move for the next solution. So it will be presented by Rama Ambu. So Rama, you are working in the University of Birmingham, and you are supposed to specialize in multi-body dynamic simulation. So please, the floor is yours for the presentation of the second use case on innovative track switching solution.
Thank you. I hope you all can see me and hear me well.
Yeah, we do.
And also the slides which I'm sharing now. Yeah.
Oh.
Thank you for the opportunity. Yeah, so I'm going to present our developments on the innovative track switching, on the switch development. So we have been developing the concept called Repoint since the past 9 years, and at various levels of development. So I'm here to present an update on what's going on here. So I will quickly run a small animation, which you can see on the left-hand side. It is extracted from the trailer which we prepared for the WCRR conference here in Birmingham. So this is the ultimate vision we are aiming for with our Repoint switch. It is a lift and drop movement, and it has a stop switch layout. And with the help of stop switch layout, we can navigate to multiple routes rather than 2 routes with the switch rail concept now. And there will also be 3 actuated bearers. Here, the point machine is embedded in the bearers, and we are proposing 3 bearers which are actuated together to enable redundancy. The aim is to is to remove any single point failure. That's what we are aiming at here. So what has been going on until now and what we are doing now within into track 3. So as I said, there are 2 main ideas within this concept. One is the actuated bearer, and another is the stop switch layout. So within the actuated bearer, we have successfully installed installed a concept, a proof of concept in Grand Central Railway in UK in 2019, and in January 2020 we had a big event where we invited industry partners to witness the development, and we also ran a train over it to demonstrate that it is working. But this concept demonstrates only the actuated bearer. It is still installed with the conventional switch rail, not the stub switch rail. And with the stub switch layout, we have only built a demonstrator in the lab scale, approximately 1 to 5 downscale demonstrator. And this demonstrate what is the stub switch layout and how it will be actuated in the stub switch layout. And within into track 3, we are planning to combine both and proceed to our ultimate goal of the stub switch layout in the actuated bearer. So there are 4 different works which we are doing, and the first is the hazard identification. So as you know, this is a disruptive entry into the whole rail infrastructure. So we have to identify the risks and hazards posed by this and take steps in advance to minimize it. So because we are doing this for the past 9 years, we have already inherited about 114 hazards passed down through generations of interaction with the industry people and also the learnings from our own. And then we selected 57 of them, which we will address within this project, and 57 which we thought it is beyond the scope of this project into track 3. And we in turn divided that into 4 which we will definitely solve, 17 of them which we will make a progress towards it, and 36 it will be an add-on. I mean, we will aim to complete it, but we are not sure if we can complete it. So this is one part of it. And the next part is the bearer assembly redesign. So because the bearer is actuated, so it has to embed a lot of components within it: the motor, the camshaft, the actuation mechanism. And in the animation here, this is the mechanism which we are going to which you're planning to install ultimately. And for this, to realize this, we have a lot of these components. And if I can go clockwise, on the top you see the complete actuation. The motor and all the mechanism is embedded within the bearer. The bearer is a pressed metal pressed metal bearer, sheet metal. And then this is the components within the bearer and the camshaft actuation, and these are some of the mechanism beneath the rail. And what I show here is the expansion joint, or the I mean the stub switch modeled in an expansion joint format. And the next task, we are doing a lot of vehicle track simulation, where we run a conventional passenger vehicle in a simulation environment through the track. And we have the vehicle model and the infrastructure model both together integrated in the software package SIMPAC. And what we get through this software is series of plots and graphs like this. So for example, what you see here is when a wheel set of the vehicle passes through the expansion joint, where is the contact patch located, and where are the points where there are less contact and more contact. And on the right hand side, you see many graphs of the forces which the rails are subjected to, the deflection which the rails are subjected to, and also what displacement the wheel will be subjected to. And in the next package, we are yet to begin this. We will develop an actuation demonstrator within the lab environment with the updated bearer design, and also with the expansion joint to see how far, to find out some learnings before we go on site. For the future, we aim for a full-scale field installation. We are approaching many companies and different organizations to enable us to install in their field and prove as be a good demonstrator. And also, if this a low traffic route, we will also be able to check the wear of the rails, and also if there are any risks, much more risks when real trains are moving over it. Yeah, those are the next steps. And thank you for your attention.
Thank you very much, Rama, for your detailed presentation on this radical new concept of switching crossing. Please stay with us until the Q&A session, Carlos. And we're going to move forward with the next presentation. So from Vincent Chartier. So Vincent, you are working from Relenium and you are deeply involved in the, I would say, work package 2 and 4. So basically the next generation of switching crossing and track. And you will present today one of the solutions that is developed in the frame of this project. So Vincent, please, the floor is yours.
So thank you, Sébastien. Good morning, everyone. Yes, I'm Vincent Chartier and work for Relenium, which is a French research institute. And I'm going to actually to make the presentation on behalf of Christian Ebner, who works for Voestalpine railway system in Austria. And he couldn't make the presentation actually because it's a public holiday today in Austria. So I'm going to present the new concept of tramway crossing, and so why studying a new concept for the tramway crossing. You can see on the picture, on the left picture, the current design of a tramway crossing, and you can notice that in the middle of it there is like a gap or discontinuity between the rails, and you can imagine that when the tramway will go through this discontinuity, it will hit the triangle point of the crossings, and so it will provoke some noise, and which is could be an inconvenience, because we are talking about tramway here, so we are in cities with people who stay close to the crossing. So yes, when the wheel hits these triangles, there will be some noise, and also it will provoke wear to the wheel, tramway wheel, and also to the crossings. So it means that you will need quite a lot of, or you will need some maintenance with cost impact, and also availability of the tramway impact, and as I said, some noise. So this new concept will aim at removing these drawbacks, and you can see on the right picture. Sorry, I think we lost the sharing. Don't we? Sorry, can you hear me?
Yeah, just a second, Vincent. Indeed, we are fixing a small technical issue to share again your presentation. So just be patient. But indeed, we see you and hear you perfectly. So
okay, great.
But by the time, Vincent, that we are solving this technical issue, I may have already a first question with you, because Rama was also presenting kind of radical, I would say, concept. And so the question that obviously coming to my mind is what, when, and how this radical new concept will reach the market. So I don't know if you have already a view on that before restarting your presentation.
Yes, so as I explained, it's Voestalpine who works on that, and the things that could be ready by the middle of 2024, because as we will see in the presentation, they are quite advanced in the prototype phase and so on.
Okay, so thank you, Vincent. I'll let you continue then the presentation.
Yes.
Thank you.
Okay, thanks. So as I wanted to started to explain, the concept, the new concept is described on the right picture, and actually the principle is quite simple.
It's just that you can see in a dark green a circular shape. So actually it is a table on which there is a piece of rail, and this table can turn and to be aligned with the rail that you want to how to say, you want to choose in order to set the tramway direction. So by this way you will remove this contact between the wheel and the triangle shape that you have in the existing in the current design. So next. So in order to, so that was the idea of the concept. So then the next step was to define the different components of this crossing. And the first one was to think about locking mechanism, because obviously for safety reason you have to keep the pivot table or turning table in the right position, and cannot move without it cannot be removed. So that they thought about many kind of locking mechanism. Finally, they find one with a pin system, and in order also to define this mechanism, where they used FEM, finite element method calculation, in order to be sure that it will work. And next, please. Thank you. And the second critical component of this new concept is to define the actuator that will turn the table. And so here again, they thought about different concepts, and finally they decided to go for an actuator based on a one shaft driven transmission. And mainly the main reason was that it was estimated that it was the more reliable mechanism. Next, please. So basically, as a reminder, so the first step was to evaluate the design functionalities, then to evaluate the components. So it was done virtually by calculation, and then to release the whole crossing design. And you can see on this picture, which is actually an animation, when you can see the turning, the pivot table turn. So could you please go on a picture? No, on the picture, yes, and move it. So here you can see the way the table turns, the sequence of the turning. So here you can see that it will change the tramway direction from the top to the bottom, and towards the right to the left hand side. So this was the principle of the whole system, how it will works. And then the next step was to make a prototype. So next slide, please. Next, please. So the prototype has been manufactured this year, and so different components were made. They were assembled, and then there were some tests, standalone tests that were carried out on these prototypes. So you can see, especially on the right picture, that the gap between the turning table or the pivot table and rail is very small. So by this way, we will avoid the contact between the wheel and the rails, and avoid the noise and the wear. So it will really increase the noise performance and decrease the wear, and so the maintenance cost. And next, please. And so finally, the next step will be to install this full-scale prototype in field. So it will be installed in voestalpine facilities in North Germany. So that they have to wait for the end of winter, and so it will be installed in April next year. And they will make some testing during next summer in order to validate the functionalities, and also the prototype will be there will be some sensors installed on the prototype in order to measure the stresses and so on. And so, as I explained before, this concept should be ready for the market around middle of 2024. And that's it for me. So thank you for your attention.
Vincent, many thanks for the explanation on this radical new concept, and also to explain where we stay on the development. Please stay with us as well for the Q&A session, and we're going to move for the last presentation on the infrastructure solution. So with Sinem Tola. So Sinem, you are a PhD student in the University of Minho, and I'll let you then presenting your last solution, sorry, on detecting score with indirect structural health monitoring. So please, Sinem.
Thank you. So I'm going to be introducing detecting scar with indirect structural health monitoring today. Next, please. Next, please. Sorry, thank you. Sorry, the one before, thank you. So the objective of this project is to detect and locate scour based on the excitation of moving loads, and through measuring the structural responses, which is affected by the reduction in foundation stiffness. So on the left side, you're seeing a typical instrumentation of a train, which is we call indirect monitoring. And on the right-hand side, you're seeing the monitoring system used in this project, which is called Riley unit. It consists of a set of sensors, including accelerometers and lasers. Next, please. So our approach consists of 3 stages. The first one is the on-bridge stage. So this is a finite element model, calculates the displacements of the points along the bridge when the train moves. So this is a moving reference influence line problem. We're using theorem of virtual works, and in the end, the apparent profile will equal to the calculated moving reference deflection. And modifying the stiffness of the bridge supports will mimic the foundation scour. Next, please. And on the stage 2, we have an off-bridge problem. So this is the calculating of moving reference response to track with different ground conditions. And the soil is modeled as a series of Winkler springs. And train on the track acts like a continuous beam supported in a series of springs. And we will be also able to model the poor ground conditions using this model. Next, please. And finally, on stage 3, we will find the bridge stiffness. An optimization algorithm will be used to find the bridge foundation stiffness, and then in the end, the problem will be finding the K, the bridge stiffness, minimizing the sum of square differences between calculated using the numerical model and the corresponding measured values of apparent profile using the Riley units we mentioned before. Next, please. So this is the data monitoring system. Riley is located at the back or front of the train, as you see right side of the screen. And it's measuring the longitudinal level. And its GNSS and IMU sensors is measuring the Z-Rayleigh line. You see at the top left green line, and the Rayleigh stripers using lasers are measuring the delta Z distance. And then their difference give the rail profile. And there are two rails. The relative track geometry are calculated using the center lines. And since Rayleigh takes unloaded static measurements, it's called located away from the axle. It's called static measurements. It's more economical than loaded measurements and track geometry cars. Next, please. So this is the bridge we've been working on. It's Carlisle Bridge, and it has 7 spans. One span is approximately 13 meters. It has 5 masonry piers, electrified ballast tracks, and continuous welded rails. It has 2 fast lines. And next, please. Thank you. This timeline is showing the availability of measurements. And we know that the bridge was repaired in 2015. It was a scour protection, the sheet piles of concrete backfill. The bridge was repaired because the bedrock scoured and the piers were lifted up off the surrounding bedrock, and the foundation courses were overhanging. Next, please. So this is our numerical model for bridge. Basically, it is considering 2 types. One is when the measurement point is ahead of the axles. The other one is measurement point is at the back of the axles. Next, please. And this is the off-bridge track. We have the springs representing the sleepers. We have the track with bending stiffness, and the equivalent stiffness of the supports are actually the combination of rail pad, ballast, and subgrade layers. Next, please. So this is one of our preliminary results. This is the moving reference displacement response of the bridge under 6 axles. This one is considering when the measurement point is ahead of the axles. And you can see the phasels entering the bridge. Next, please. This is type 2, when the measurement point is at the back of the axles, when Rayleigh unit is located at the back of the train, namely. And here you can see the front axles leaving the bridge. Next, please. This was the scour simulations we did using the bridge models. So the blue line shows no scour, the red one shows 50%, and the green one shows 75% of scour. Next one, please. And this one is the moving reference displacement response of the railway track. And right now we are working on a reduced stiffness zone you see at the bottom. And then we will have the opportunity to relate the measurements with ground conditions. Next one, please. This is our measurements to give you an idea. So you can see one run, or in some cases other tracks, more than one runs are different from the general trend. So right now we think that the reason for this is due to different weights of trains in different runs. But we will have more and more clear idea when we have the raw data. Next one, please. This is a little bit of frequency domain analysis on measurements and also on simulations. So we calculate the maximum spatial frequency, and we saw that using the ones we calculated from measurements and the simulations are equal. Next, please. Yes, and our next step is finally having more robust mechanical parameters of the vehicle. So we will use Monte Carlo simulation to generate these parameters. And then using a vehicle bridge interaction model, we will simulate the apparent profile. And then using those apparent profiles, We will train a machine learning algorithm to have, again, mass and stiffness parameters. And then we are expecting to have more accurate calculations, more accurate displacement. And in the end, we will develop a damage indicator to prove the existence of scour, and it will be the function of displacement. And yeah, knowing the actual train rate will improve the damage indicator because it will reduce the scatter. Thank you. Thank you for listening.
Thank you very much, Sinem, for this presentation. I'm inviting then Vincent, Rama, and Carlos to join the session for the Q&A. Okay, super. And Sinem, obviously, inviting you to remain with us. So my first question will be actually for you, Rama. So you were presenting, as mentioned previously, a radical solution for point machine. So what do you think are the main benefits of the solution to compare conventional switch solution?
The main benefit comes with the single point actuation being removed to multiple point actuation. So what we feel is there are a lot of network delays and maintenance problem and a problem of insufficient movement of the switch happening. And if the point machine fails and then someone has to fix it before the network is back on track. So these issues can be overcome when we have multiple point machines, and also not with the linear movement, but with the lift and drop kind of movement. So that's the main benefit we are bringing.
Thank you, Rama. For the benefit of time, I will go only for a last question to be for you, Carlos. So you presented earlier the development and well advanced development actually of the 3MB system. However, what are the next steps that you foresee in order to have the development mature for the market uptake?
Yes. So as I mentioned, the system is going to be online up to 2024 if everything goes as it should. With all the information that we're going to gather, we should be able, on the one hand, to advance the safety case that we've developed to acquire the permission from Trafikverket and the Swedish Transport Authority to install. So that would mean that the system would be homologated for the Swedish market. With that, we expect that we could convince other infrastructure managers to install the system at the very least in small sections for testing, since we have first-hand information on its validity. And with that, we should be able to launch it to the market in a short period of time. Also, we're thinking about making adaptations for tunnels and bridges, for example, in which it could be thought out that the base lab wouldn't be necessary because these infrastructures already have their own slabs, as it were. And there's still maybe some work to do for the tighter curves, because the system has been tested in a straight section. So those are mainly the next steps that we foresee.
Very clear, Carlos. Thank you very much. And thank you very much, the four of you, for your very interesting presentation. We are going to enter now for the last cluster of presentation dedicated to the Intelligent Asset Management System. And to introduce the topic, I'm pleased to welcome Carlo Crovetto and Hank Sampson. So Carlo, you are with us since 2014 and coordinator for the Into Smart series. And you, Hank, you are the TD3, that the 8 leaders working for Structon Rail, as a senior program manager and the business development and innovation unit. So welcome, Carlo, welcome, Hank, and the floor is yours for this introduction on YAMS.
Okay, good morning, everyone. Can you hear me? Yes?
Perfectly, Carlo, yeah.
Okay. Okay, good morning. As Sebastian recalled, I was the coordinator of Into Smart 2 and also previously of Into Smart, whose acronym stands for Intelligent, Innovative, Smart Maintenance of Assets by Integrated Technologies 2, which actually seen in retrospect focuses too much on maintenance rather than with a broader view on asset management. Despite that name, several use cases or let's say demonstrators dealing with asset management approach have been developed in the project. And today a small selection of which will be subsequently proposed by some partners of the project itself. The Into Smart project, sorry, next. Okay. The Into Smart project started on December 2019 and was grafted onto a path that originated in the now distant 2015 with the Into Rail Lighthouse project. Continued in 2016 with Into Smart, and always during the developments there were exchanges with the relevant open calls. Next, please. Okay, the project had its final event in Milan on last November 9th in the prestigious location of the Leonardo da Vinci National Museum of Science and Technologies. And on that occasion, all the asset management demonstrators were shown, widely varied in type and purpose, and they were developed in the different working packages. As I mentioned above, a limited selection will be presented later. Next, please. Okay, the time available today only allows me to focus on the fundamental aspect of integration of all these developed use cases, which is related to the architecture. Conceptually, there are two bases on which it was conceived. That we are sharing data using a common conceptual data model, and managing as well as processing the data using a common integration layer with standardized interfaces. Next, please. To conclude, I just wanted to introduce the concept of the three layers, which are the basis not only of each of the demonstrators developed in Into Smart 2, but of the very concept of asset management. With a bottom-up approach, a first level to collect and group data, creating a data lake. A second layer to perform on those data analytics and extract knowledge. And a last one on the top to focus on decision-making and strategy. So thank you everyone for the attention, and I am now leaving Samson the burden of deepening the analysis in his role of TD3.8 leader.
Okay, yeah, next slide, please. Yeah, what I would like to highlight, in addition, what Carlo already introduced, because basically he explained the whole pillar of three TDs, TD 3, 6, 7, and 8. However, in TD 3.8, we have what you can see on the right-hand side illustrated with some images, the decision support based on the two other TDs. But there's one other element which I would like to emphasize, and that is actually not only the decision support in TD 3.8, but also the actual execution. So this actually took place in context what is later being being presented by Amanda Hall about the robotic exercise we did into Smart 2, but also the presentation that Christian Di Natali will give about the results from the STREAM project, so that you understand that the execution part is actually also part of this TD38, and therefore there are some other developments being presented as well. That's where I would like to leave it very shortly for now. However,
hello, Hank. Thank you very much for introduction. Hank, I'll leave you the floor to continue with this first use case on the operational asset management in a Dutch environment. So please continue.
Yes, so what we see here in this slide is actually the integrated demonstrator, which we try to do in IntoSmart 2 work package 12. And again, you see the three layers here. So part is the data acquisition, the other part is the data analysis, and finally, there's also the planning part that we have here as well. We try to illustrate here the individual components of work package 12. But we need this context, because then I can highlight later different scenarios, so how the different components actually relate to each other and how we come to finally plan actions outside as well. It also illustrates the need of doing this. So first of all, assets are aging, we have less people, people are getting older, so there's hardly any new staff, we need to be more efficient. Also, we have some contractual implications. So as a contractor, we get more responsibility. So within our maintenance contracts, we take more responsibility, which means we need to understand the behavior of the assets ourselves better. Another thing is that foot patrols are not possible always because of increasing of safety restrictions. Furthermore, there's a growing demand of transport and the reliability of it, and we need more efficiency. What we also need is to harmonize and reinforce the domain knowledge. So that is our objective, which is illustrated in this image on the right-hand side. We want to have a smart use of the possessions that are available, and they are limited, which means we need to use that time very smart. And another thing is all this digitalization helps us also to improve our accountability towards our client as well. So next, please. In this slide, we use the same context of the individual developments. However, we place them into a context, as I said. And here you can see the flow, in this case, from the switch monitoring and how that leads to actions outside into the possessions. So that's why we need also our planning developments as well, in order that what we actually derive from the prediction models from our switch monitoring, so that we get that more effective use of this. So next slide. In the next slide, I won't focus on the prediction models as such. We have worked together with DLR on this. What we have done with DLR is to improve the prediction models by adding a lot of data sources like humidity, temperature, etc. So to make the models more reliable. What you see in this image is actually that we have come to further steps and a workflow, so that in the back office we can work more efficient, so that we can digest all that knowledge and actually come eventually to actions. So if you go to the next slide and start the video clip on that. Next slide. And this is a small video clip just giving some screens. So this is a very dry PowerPoint presentation, but we actually have developed software tools so that maintenance engineers have easily access, in this case per switch, to the data and can actually assess this. Okay, the screen doesn't say too much, but it gives also clues what the difference is in the current that we show on the screen, actually what the deeper cause of that is, so that they can easily assess the reasoning behind it and actually come to maintenance actions that should be planned in the next possession. So if you go to the next slide. No, next slide, please. Yes, this is another scenario. In this case, we use train-bound data, and we look specifically at fastness. So working in this team and very close to our daily operation, we suddenly got the urgent request to look at fastness. So next slide. What happened is that the requirements of monitoring the fasteners outside have been increased. There was obviously an issue that fasteners seemed to be loose, and we needed to have action, or have to actually to check all the fasteners. Now we can send people outside, but like I argued, we have limited time to do this by lack of people, but also the possessions are not available. So our operation was saying, we have so much data, isn't it possible to look at the fasteners and that we can actually crack this problem? So we looked at the video images that we had available, and we found actually that we can identify the rail foot and also the position of the fasteners. And when it is a little bit out of position, or actually beyond the threshold, then it would actually be regarded as being that it is loose or not. So we were able to anticipate about this urgent request from the operation. So next slide. So by illustrating now the multi-use of our train-bound data, so we have multiple data sources. So if you go to the next slide and start also the video clip for this. Yeah, so this is a small video clip without sound, and I will talk through it. You can start with it. Yes, thank you. What we have done under the name of Leonardo, we use an old tamping machine. This is not the old tamping machine, but this is the old tamping machine, where we actually used our sensor equipment, but also were able to add different cameras, as you can see here. So here you see the different camera views that we obtain by using this tamping machine. So we were able to experiment with different cameras, so we could also see the overhead wire. And we easily could experiment with it in operational track by driving 90 kilometers an hour. Now, having this data, you need to have an interface by putting this data into the same context. So the exact location, so you can see on the left-hand side the geographical information system, but then also the images. We get a Google Earth view on this. We can also recognize different types of objects, as you can see here. We are also able to use the images, and that we actually can measure parts of the images that we can see. So here you can see in the control center the use of these images. This is more traditional data that we get in as well. But we use heavily the video images in combination with other data. Now, this is more an outlook. Here you can see the use of a ground penetrating radar. We didn't use this in Intersmart 2 explicitly, but we're going to use this shortly. And we, of course, used also LiDAR data, as you can see here, because that made this able that we could do actual measurements outside, meaning actually that a lot of people don't have to go outside anymore. They can actually measure bits and bobs that they need by planning renewal projects. Last but not least, we use the old tamping machine, but we can also use the equipment on alternative vehicles like lorries, meaning that we can also go to different networks like a metro network or tram network. So this is what we actually did, do the data acquisition, and now we are going to use the data. Next slide, please. To highlight one of the scenarios I already mentioned, that is actually for the renewal project. Next slide. So on the renewal project, we used the video images, as you can see above, to generate the redesign of the track layout when we perform a renewal project. So we don't have to go outside. We use the data that we obtain from the Leonardo vehicle, and then are able to use this data in combination with CAD systems in order to make the new track layout. Next. Last but not least, the planning. We looked at the planning in two different ways, more strategically, but also more operational. So the first one is about the more strategic view on it. With that, I mean that we have a time horizon for many, many months in advance, and that we look at our total workload and the people, the resources that we have. So if you go to the next slide and click on the video clip that it will start. So what we do here is we look at the different regions that we have, both renewal projects, but also our maintenance contract, and we can map the track possessions, so that is when tracks are available for us to perform our work, and also look at our resources and how that matches together. This gives just the gist, so the different tools that we have developed. We have some different screens as well. It goes too far to go into too much detail right now. So this gives us a feel what we need to do resource-wise in order to digest the workload that we have coming up to us. Now, another time horizon that we take, and if you go to the next slide, that is more operational. So with that, I mean that from the back office, we actually get information what the actual status is. And in our maintenance projects, we then need to plan our possessions, the actual possession from, let's say, in 2 weeks' time. So who's going there, but also which actions do we have to take? And if you take the final slide, indeed. So what we do here is based on the predicted condition from, for example, the switches, but also the other items that we have been able to assess based on the data that we have gained, we can actually then plan our possessions more carefully. So besides the work that was originally scheduled, let's say for a year ahead, we need also to anticipate on the risks that we suddenly see in the short term and to make the track more reliable so that we know that a certain switch, for example, or the track alignment is not correct and might cause disruption in the near future, that we do this before it actually happens. So we look at the risks. So initially we looked most of the time at the tamping and the different kinds of tamping that was we were able to do to anticipate to correct the track alignment. So that includes also that the availability of the machines and the people, but also the time that is needed to go to the exact location and how many of those locations can you do in one possession, looking at the different types of tamping we could perform. So the whole optimization problem is rather complex. So this is in a nutshell the different topics that we tried to put into place and to reach high TRL levels. I forgot, of course, to mention all the partners that have worked on this work package, and I also did do injustice to some of the work and the complexity that is done behind it because I had to make choices. But we worked together with Siemens, we worked together with Somoza and Fraunhofer on the planning topics. We worked together with DLR on predominantly the switch monitoring, but also, for example, the axle box accelerators, by the way, which didn't reach that high TRL level because it needs simply more research, which is actually very nice that we can work in a multidisciplinary team. So with my own colleagues from Structon being very close to the operation, including suppliers from good technology, including researchers from the research center at Fraunhofer and DLR, as I mentioned. And I would like to keep it here. And I hope I have been in time, because otherwise I lose a bet.
Thank you very much, Hank, for your presentation. And as per the previous cluster, please stay with us until the Q&A session. I would like to invite now Amanda from Network Rail to join us. So Amanda, you are a system engineering expert working for Network Rail, and so you have been working in the rail industry for almost 30 years now, and you are currently involved in research and innovation development. So that's the reason you are here today to present the use case on the robotic and automated lean execution. So please, the floor is yours, Amanda.
Thank you. Can you hear me okay?
Perfectly, yeah.
Lovely. So next slide, please. So what we have been doing in work package 13 of Intersmart 2 is to take the work that was done in Intersmart 1 in this area and take it further. So it's to further develop the command and control aspect of autonomous robotics up to TRL 7 and showcase it during a track possession. Another part of the work was to develop an end effector which can screw and unscrew track fastenings from a robot. And another part of the work was to use the same command and control principles as for the network rail and Cranfield robotics, to use the same principles on a different machine to show that that can be done. And that was done by Traffic Verket and Chalmers using a different type of vehicle. And you can see the 3 photographs there. And I'd like to show you a short video of the demonstration testing that we did for the Network Rail and Cranfield piece at Northampton and Lamport Railway, which is a preserved railway in Britain. Can you run the video, please? This project is with Shift to Rail. This particular programme is InterSmart 2. We thought, wouldn't it be nice if we could have an autonomous robotic system that would be able to carry out some fairly basic inspection and maintenance activities, the sorts of things that are quite easily repeatable.
Some tasks that we actually do are better suited for robots than for humans. So you can have a safer environment, you can have lower costs, and you definitely will have better reporting.
I was involved in the very initial steps to look at whether robotics would fit into the operation of the railway, decide what operations could benefit from automated robotic systems, and then start to develop the command and control system, which we're developing here.
We are on a heritage railway. There's no other trains on the track, but we are able to test the vehicle over longer distances to ensure that the communications, the navigation and location, and the detection of the simulated faults are all done in a proper railway situation.
This is our robotic inspection and repair system. It has 2 parts. One is called Warthog. It's an unmanned ground vehicle, and they also have a track trolley. And the front, we have a stereo depth camera to give the distance of the front obstacles and trackside obstacles.
At Cranfield, we have a team of researchers. We've got some full-time research fellows whose job is to work on certain aspects of the project.
The navigation of this vehicle will be based on GPS and autonomously, and it needs to be specified in absolute level of accuracy. We applied RTK GPS in order to provide us global level of accuracy.
At the top, it has a 3D laser scanner, which is called 3D LiDAR, to give you the point cloud of the surroundings. Last but not least, it has a robotic arm. It has a manipulator camera to give you a visual inspection.
I can tell the arm how much it should move in each joint. So the robot arm has a total of 6 joints. We can define how much each joint should move.
What we're using to simulate railway faults is a number of pre-printed QR codes. Then the robot's cameras pick up the location of those and record the data of where it's moved and how it has undertaken that inspection.
We have 3 different QR codes. So one will be defined as the old defect. It will just send a message and move back to its initial pose. When it finds the type A defect, it will take pictures. And when it finds the type B, it will also save some GPS location so that if anyone wants to inspect it further, they can use the GPS location as a reference.
We can detect objects and especially people as the robot approaches working areas. We've added RGB depth cameras to be able to identify closer objects, and that's added to the robot's original capacity.
Today we have seen very successful tests. We have been able to do the simulated work orders, and we have also been able to perform some unplanned simulated work orders.
I'm immensely proud of everyone who's worked on this. We've had a huge team from Cranfield University, Network Rail, Structon Rail, Traffic Verket, and together we've managed to come this far. Here we are today, a success.
We've returned to the site at the Northampton.
I
We have a
don't
small
know what's
disruption
happened
in the,
to the video.
yeah,
It
probably a
seems to
small
have stopped.
disruption, yeah.
And push that onto the track.
We have 3 types
of original capacity.
Today we have seen very successful tests. We have been able to do the simulated work orders, and we have also been able to perform some unplanned simulated work orders.
I'm immensely proud of everyone who's worked on this. We've had a huge team from Cranfield University, Network Rail, Structon Rail, Traffic for Kent, and together we've managed to come this far. Here we are today, a success.
We've returned to the site at the Northampton and Lamport Railway to demonstrate actuation of the robot.
The tests today simulate a maintenance task being sent to the rail robot from a central maintenance system, the robot travelling to that location to then go into a creep mode to find the actual fault. That fault is demonstrated in terms of a QR code. The specific QR code will tell the robot what action it needs to take, and that's demonstrated by the 3 different boxes full of different equipment. Then it'll pick one of the boxes and push that onto the track.
We have 3 types of gear code, one with some electrical instruments, one with some tools, and one with pendurals. So once the robot finds the defects, it will recognize which color it is and what object it should drop.
My name is Isidro Durazo Cárdenas. I'm a lecturer at Cranfield University. I support the work that we do for Network Rail. It's much safer to use robots to do these kind of jobs. There might be traffic involved, so they're specifically tailored to do these sort of repetitive, hard jobs.
In the future, the intention is that a fleet of such vehicles will be able to respond to faults which have been indicated either by human inspectors or by measurement trains, to investigate the faults further and to make interventions and further surveys on the spot, completely autonomously.
We're very proud of our researchers, our PhD students and our MSc students, because they contributed enormously to the development of this technology.
What we wanted to do was to make sure that we had achieved everything that we wanted to do within the auspices of Intersmart 2.
I am very proud of being able to interact between the private and the public sector and being able to bring solutions to problems that exist in real life.
Thank you. That's the end.
Amanda, thanks a lot for your presentation and also this video that is presenting a lot of details about the challenges you are facing, but also the way the platform is operating. So thanks a lot for that. Stay with us for the Q&A session. I will invite now Marco Borinato to join. So Marco, you are a software engineer in Hitachi Rail, and you have also a role of TD leaders at TD 3.6 and TD 3.7 into the Europe's Rail program. So please, the floor is you to present this 3rd use case.
Thank you. If it's okay, I will start sharing my screen.
Please, yes.
And starting now the presentation, please let me know if you...
We do see the charts and not the presentation, indeed.
Perfect. Okay. I will today guide you through very quickly to work package 5 and the development that we have achieved within Intosmart. And then we'll have a small demo of the achievement by Daydreams, which is an open call of Intosmart 2 that has collaborated with us in work package 5 to develop prescriptive functionalities in the analysis of track circuit data. A little bit of context of what is work package 5. The goal was the implementation and testing of a complete intelligent asset management system within the environment of the urban metro 5, line 5 in Milan. The objective that we have reached are the collection of data from different wayside and onboard system, providing capabilities for trend monitoring, alerting, and the development and deployment of detection models to predict, so to provide predictive capabilities on the forecasting of asset degradation and the asset status. We have then provided our partner ATM, the Azienda Trasporti Milanese, with a complete HMI that supports them in the planning of operation activities in the line. And the testing and the project is finished, but the platform is still operational and used by ATM. I want to highlight the fact that this work has been done in collaboration between our partners in Work Package 5, which are Simosa and Fraunhofer, other than, of course, ATM for the system provider. In this context, we have the collaboration with Daydreams, which has provided a switch to a prescriptive approach in the analysis of data. Why the prescriptive approach? Because it can answer not only a question like what is the problem and where is it happening and what is the cause of the problem, but also can support the operator by giving suggestion on what to do. So providing additional support in the maintenance process by suggesting already predefined metrics and let's say improving defined KPIs. The scenario addressed by Daydreams are multiple. As you see here, we will focus on the first one, which is, as I said, the management of track circuit in a metro environment together with IntoSmart. As I said, the objective of the Daydreams are to improve and make more robust the prediction of status of assets, in this case only track circuits, to support the operators, but also the step ahead is the using of prescriptive analytics and multi-objective optimization in order to provide not only additional information, but also additional suggestion to the operator, improving defined KPIs, such as we will see in the demo, maintenance operation duration or the cost of the operation. These achievements have already been achieved, and the developments that Daydreams has produced is also, let's say, applied in the Metro Milan Line 5 use case, and ATM again is providing feedback on the use of the tool. So we will move now directly on the visualization. You are seeing the charts and the web interface, correct? Sorry, I cannot hear you.
Yes, we can see the chart.
Okay, perfect. So this is the web interface that Daydreams has provided. As you can see here, the interface is the same for also the other use cases. We will focus, as I said, on the Hitachi use case, so Work Package 5. Here, the operator, which uses the interface, can visualize the different plans that the software provides. These plans are constructed based on the results of the analytics algorithm that we will show a little bit further ahead. And they suggest, so they apply a predictive approach, suggesting which are the assets to be maintained and how to schedule the maintenance. By selecting one of the charts, for example, these, as you can see here, you have a KPI matrix, basically telling you what is the maintenance cost to maintenance duration ratio. And by this graph, the operator is immediately capable of seeing which are the best maintenance plans. For example, this obviously is not the best one. The best one would be somewhere around here. Obviously, the operator can then select different KPIs, for example, robustness, to visualize the different plan in that context. We will move back to maintenance cost. By selecting one of the plan, as I said, the operator can then drill down on the right, seeing which all the KPIs, how the selected plan addresses each of that KPI. And most importantly, is presented then with a calendar, let's say, view, where the software automatically apply the multi-object optimization and schedule for the operator, provides a suggestion in the scheduling of activities. The red one that you see here are the corrective suggested activities, while the white one are the preventive activities that the operator has already scheduled, so that let's say cannot be moved or changed by the algorithm. What the operator instead can do is move freely the different corrective intervention. By doing so, he modify obviously the KPIs and the computation, and we see this reflected in the map over here. This is done because obviously this use case focuses only on track circuit management, but by applying it to the real world, it can easily be integrated with all the different maintenance procedure and be integrated obviously with the other activities that are planned on the area. As I said, these maintenance plans are based on the categorization of the track circuit between faulty and healthy track circuit. The operator has also the possibility to visualize that more freely in this interface, where visually you can see the whole line, Metro Line 5, very basically in a basic representation, and you can see the different track circuit. The algorithm provides a prediction on which, again, the plan is based, telling you if the algorithm expect the specific track circuit to be faulty in the next 2 weeks. So we can have a differentiation between healthy track circuit that will not become faulty, and then a prediction on the anomaly, possible anomalies on the track circuit. This is the important part, because this is still a predictive approach, we can say. But if we go more deeply into the different models that provide the prediction, we can see, for example, this is here we have a list of different models that provide a different functionality. If we, for example, drill down on the failure model for the prediction of track circuit, the model provides the main feature in the decision of making the decision between healthy and unhealthy track circuit. These features are, let's say, characteristic of the line of exogenous data of the track circuit. And moving back here, we can see the binary decision tree, which is basically provides the operator with an explanation on how the algorithm makes a decision. For example, here each node is a specific feature. For example, here the number of loss of occupancy, the month, so also the period of time is an important feature in the selection, in the characterization of faulty or healthy track circuit. And by simply following one of these paths, we see what kind of prediction we have. For example, a class 1 means an unhealthy track circuit, while a class 0 means an healthy track circuit. And we can understand which are not only the main feature, but how their value impacts on the classification of the in this case, the track circuit, but in a general approach, the asset. So this is the main additional values that the Dreams has provided, and is a very important switch, because we move from black box approach in machine learning model to a more open and human interpretable approach. This, as I said, to conclude the presentation, this work will be done continuously in the next month, and for the duration of the Daydreams in 2023, and we will have also a real test in the real environment in Metro Milan. So thank you for your attention.
Many thanks, Marco, and stay with us for the Q&A session. Now we're gonna jump directly with Christian Di Natali. So Christian, you are a researcher at the Istituto Italiano di Tecnologia, and you're also the co-founder of the startup Poteso. So please, the floor is yours. If you can make it in 10 minutes, perfect. Thank you.
Yeah, thank you. Are you gonna show my slide, please? Could you hear me well?
We do, Christian, perfectly.
Okay, so first of all, thank you for the opportunity to present here the project stream at the Innovation Day. I will go through, try to present a few essential aspects of the project. And yeah, STREAM, first of all, stands for Smart Tools for Rail Work Safety and Performance Improvement. Say next slide, whenever you can manage it. Thanks.
It's a small technical issue, so please continue with the introduction of the project, no problem.
Yeah, if you can show the second slide. Okay, so STREAM is an open call that started at the end of 2020 and will end in May 2023. There are 7 partners from 5 different countries, and the Istituto Italiano di Tecnologia is the coordinator of the project. Next. So how is the consortium structure? We have 2 main technologies developed by 4 companies or research institutes. The first one is developed by Tampere University and Novatron, while the second is developed by Istituto Italiano di Tecnologia and STAM. We have the COMSA as an end user, and the exploitation is carried out from Novatron and IIT. The supporting activity, such as acceptability, economic aspect, and dissemination, are carried out by Grenoble Business School and Unife. And finally, you can see on your right side of the slide our end user board, which is composed by several companies. Next. So the objective of the proposal are the improvement of safety and working condition, the reduction of process cost, the improvement of quality and accuracy, and thanks to our technology, we would like to make a manual activity less demanding, thus obtaining those job duties be more sustainable and attractive. Next. So this figure represents and synthesizes the main technology we developed in STREAM. So we have a robotized machine. We have workers wearing exoskeleton and IoT network that shares data gathered from those 2 technologies to improve both the control, robotic control, and worker safety. Next. So the project is divided into 5 phases, during which we alternate development and testing validation. The final goal is to reach TRL 6 for both technologies. Next. So these are the use cases of our interest, and as you can see, we focus on the ones where both the excavator and manual activity were involved. We are considering maintenance and renewal operation mainly. So then we analyze several of those use cases, and we generate specific solution able to improve the specific working operations. We will see in the next slide few results. Next. So this is the first technology. We call it OTA 3M. This is a control platform that could be adapted to any excavator. This control platform can convert traditional excavator into robotic system by adding actuator, sensor, and computer to run specific control algorithms. So the main objective is to develop such technology to enable a supervised system or even a fully autonomous machine. So in Stream, we target the development of the most complicated concept, the full autonomous system. And we define two operational modalities: the working mode, when the excavator moves its arm to accomplish specific tasks, and the running mode, when the excavator keeps its arm retracted and moves along the rail from point A to point B. Next. So this movie clip represents the ability of the system to detect moving objects. As you can see, the system can detect the object, but also it can measure its location from the excavator position. So this feature is very important when considering the ability to control the excavator accordingly. Next. So this KPI shows the ability of the controller to avoid restricted space. The system control the excavator boom thanks to the control algorithm combined with the building information model. So when the control is enabled, you will see around the excavator boom blue area. When the blue area and the red area goes in contact, the system understands that that direction of motion is not allowed. Thus, it prevents accidental crash against piece of infrastructures or possible movement across restricting areas. The example we provide on this video with the railway on the side, as you can see right now. Next, please. So this is the last result I'm showing about this technology today. These videos show the ability of the controller to understand the amount of transmitted force on the infrastructure. The transmitted force is directly correlated to the instantaneous position of the excavator arm and the weight lifted. Therefore, the system is able to control in real time the maximum reach of the excavator boom to prevent overload to the below railway. You see on the video the red columns around the rail interface that are changing, that show the amount of force transmitted to the rail underneath. Next. So moving to the second technology, this is an exoskeleton that workers wear. This exoskeleton is an active device with electrical motor, sensor, and a computer on board. The exoskeleton has been developed, adapted, and customized for rail workers and rail applications. The device is tailored to rail requirements to support workers during manual material handling. It is able to understand human activity to deliver a personalized assistive strategy. So the main goal is to develop such a device that can reduce the musculoskeletal system overload, allow workers to experience less fatigue, and at the same time reduce the risk of injury. Next. So far, we have selected a specific use case, as you can see in the slide, where workers were performing lifting, transportation, and fine positioning of those concrete blocks. So this is a very transversal activity, and many other activity require lifting heavy object like this. Next. So we set up a real environment simulation with several workers. We replicate the test with and without the exoskeleton to evaluate the performance. The test was an hour long for each modality. Then we moved to the laboratory to apply motion capture techniques and gather the measurement of muscle activity for each work task. Next. So we estimate the reduction of muscular activity that ranges from 15% to 22% for those working tasks we selected. Next. So then we combine observational measurements and laboratory measurements to extract the reduction of lifted index. So the lifted index is a typical measurement that correlates the ergonomic risk or the risk of injury and the manual material handling task. So we estimate an average reduction of about 52% for the lifting and carrying activities, moving the risk from high to low. Next. So then we measure the metabolic cost and evaluate the reduction using the exoskeleton. The test duration was an hour long for both modalities, with and without the exoskeleton. So we replicate these tests for 5 workers in 3 different days each one. So we cover about 3-4 weeks of test on relevant environment. Next. So the results shows that thanks to the exoskeleton, the activity moves from vigorous activity to moderate activity. This could be simplified as without the exoskeleton, it likes to climbing stairs for an hour, while with the exoskeleton, it's like doing gardening for an hour. What do you prefer? I guess you will choose to do gardening. Next. So this is the last result presenting today. So we measure the execution time for each cycle of the test I just presented. So the evidence shows that even if the worker was not wearing the exoskeleton and was starting at high speed, so we are looking at the graph on your right side. So in blue, it's the in average, the worker without the exoskeleton. So they were starting quite fast, about 3 minutes per cycle. So what happened after about half of the test, so after 30 minutes, they require a break. So you see a spike on the blue line about the 10th repetition. And then again, a second spike about after 15 minutes, so about 45 minutes after the beginning of the test. So for a second break. So when instead the worker was using the exoskeleton, the worker did not need any breaks. You see that the red line represent this the average time for all the repetition we did of our test while the worker was using the exoskeleton. And so the variance is very low. And at the end of the test, the average execution time was very similar with just 9-second difference between the two modality. Moreover, the worker with the exoskeleton was not tired. You can see this on the chart on the left side, where we use the board scale to measure the perceived exertion. So without the exoskeleton blue, the exertion was moving from 2 to 3, about that values. So from moderate to high fatigue. Using the exoskeleton, the workers were say that the fatigue was reduced after an hour. So from moderate to low. Next. So thank you very much. So if you have any question, you can also reach me at this email, christian.dinatali@iit.it. Thank you again.
Christian, many thanks for your presentation. We are now going to a very quick Q&A session. So I'm inviting all the YAM speakers to join me on the floor. And the first question for you, Marco, as a TD leader. So basically, how prescriptive approaches in the asset monitoring could improve the overall maintenance process?
So basically, as I said in the presentation, prescriptive approaches suggest not only what is wrong to the operators, but also they provide a broad suggestion on what kind of application or activity they should do. This is very helpful in their work because they can prepare for a specific intervention or a specific activity, while always keeping the, let's say, the final decision to the human operator and not the machine. And this is a very important aspect of the work. And we plan to address this topic more in details in the development of Europe's Ray next flagship projects.
Thank you, Marco. My second question will be for Amanda. So Amanda, from your presentation today, we understand there is still some work to do before your solution being ready for the market. So what are the next steps you foresee into the development of the platform?
Thank you. I think for us, the next steps are partly technical, but also around the rules and standards to allow the use of autonomy on our railway. So in order for us to have products that gain product acceptance, then we will need to apply the common safety method. And in order to do that, then the robotic operating system platform that we've used for the development is version 1, and we will need to transfer that to version 2, so ROS 2, in order to have the ability to make safety arguments from a system safety perspective for applying the common safety method. And I think that the other thing that we'll do as part of that is to develop a technical requirements specification so that we can go out to the market and buy things that do robotics autonomously successfully in the railway.
Thank you, Amanda. And my last question will be for you, Hank, in 1 minute. So you have been involved now for several years into the Europe Shift to Rail program. And so the question is quite broad, but otherwise quite targeted as well. So what are the lessons learned you would like to mention today based on the different development you have been involved?
Well, the projects always have a clear focus, so we set certain targets. But the main lesson learned is that we are sometimes able to anticipate on other requests, as I argued during my presentation. So suddenly there might be more quick wins available, and that actually some of the targets that you set seem to be more complex and could be a little bit disappointing. But so you still need to focus on those targets as well, so by further research, for example. But at the same time, it would be interesting to explore the different possibilities that the technologies that are already available or the data that is already available could have in the current practice outside. So there are quite often more quick wins than we quite often could anticipate on. So we need to be a little bit more agile in our approach and pick up those quick wins as well.
Okay. Thank you very much, Hank. So we are now reaching the end of this session. So I would like to thank all the presenters for your availability this morning and also the quality of your presentation. I would like also to thank my colleague Anaïs and Pauline for their very good work in terms of presentation preparation that have been ensuring a smooth session this morning. We are going to circulate a survey as of Friday, 9th of December to collect your feedback to enable us to improve our events in the future. So please try to give a feedback thanks to this survey. We are also inviting you, if it's not yet done, to subscribe to our mailing list by visiting our website. We are now going to break for lunch. We are going to restart at 1 p.m. Central Europe time with my colleague Goraz Marinic that will present you the main achievement of the IP4 ecosystem. So for this session, there will be a different link that this morning that you can find on our website. So thanks again for your presentation. Thanks again for all the attendees to have been with us this morning, and wish you a pleasant lunch and a good continuation within the Europe's Rail Innovation Days. Thanks a lot. Goodbye.